Aiden. Aiden? Aiden? No, Aiden. Aiden. Yeah, I saw that. Is that? Can you get to it from here?
As long as I sent you the email and it's on my email.
So we'll go to your email. Okay. Yours is probably easier to get to than mine. No, I'll get you in about 10 minutes. So today, let's see, your homework 2 is due by midnight tonight. Hopefully you'll get that squared away if you haven't already. I remind you to make sure that you're reading the book. I can't emphasize enough. There's no way I can cover every little detail of C++ that's covered in the book in class. I don't even try. So it's up to you guys to read and make sure that you're picking up all the little details that I'm not discussing in class. What I thought I would do today is a really brief bit of Vim. Just one sec. We'll talk a little bit about Vim. Then Aiden will do his presentation. Then I will discuss and demonstrate the homework 3 program. Then we will move into Boolean expressions, more advanced Boolean expressions. And if we have time, we'll talk about more general loop syntax. Yes?
So when you say for the reading, is that our homework for that night, or is that what we're going to discuss on that day?
I try to discuss this reading this day, okay, but I'm already pretty sure I'm not going to get to 3.3 today. Okay. But generally it's in parallel, and by no means will it hurt you to have read it in advance, or perhaps even to have read it the day after I talk about it. It's all just sort of running in parallel with the lecture. Okay, but I don't promise that it matches up perfectly. But again, in particular, the programs that I'm assigning use material from the readings that I might not talk about explicitly in class, and that's the thing that I want to emphasize. So, a 10-minute Vim lesson. So, I've had a chance to watch some of you guys use Vim before my very eyes when you're in my office asking me questions or whatever. It's good. Some of you have really kind of taken it to heart and looked at what some of the things that you can do beyond just sort of moving around and inserting and escaping. But I thought I would start giving you some more advanced stuff. Let's see here. I want to go here. Let's go here. And we'll just look at an old example. Another thing, if you're using, if you are using putty and you highlight something, you don't have to hit Control-C to copy it. As soon as you highlight it, it's copied. And then if I hit the right mouse button in this window, it's going to paste it. So as soon as it's highlighted, it's copied. And the right mouse button will paste. That can save you a bit of typing. And for example, if you're over in Chrome, and this is not something that you would want to do, but let's say you went to Google and you for some reason wanted to copy this, you could copy it and then go over here and then just hit that right mouse button and it'll paste it. So in Putty, the right mouse button is paste and highlight is copy right off the bat. No Control-C, no Control-V. Yeah.
Does that work in Terminal too?
In Terminal, it's a little bit different. In Terminal, I think you're stuck with Command-C, Command-V.
But you can still copy straight into.
Yes, yes. But I think you have to use that command, that Mac command key. But to be honest, I don't own a Mac, and so I don't know the real low-level quirks. I've been meaning to get a Mac just for the purposes of this class, because there's so many people now that use them. I feel sort of left out sometimes when I don't, or less than useful when I can't answer Mac questions. All right. So let me, I don't know, it doesn't really matter here. I'm just showing Vim, so I'm going to look at this file. All right, so I think most of you have got the idea that you can move the cursor around with H, J, K, and L. And when you get to a point, and if you hit I, it's going to put me in insert mode, and those characters are going to start appearing before the R, right? And if I escape and I go here and I hit A, then the characters are going to start appearing after the R. So I think most people have that figured out, I and A. Capital I will start inserting at the front of the line, and capital A will start inserting at the end of the line. So those are also useful variations. If you want to get rid of a character, like I don't want, say, the backslash T, I can put my cursor there, and do you know what the command is to get rid of that character? Those are definitely ballpark, but if I just want to get rid of that backslash, I can hit X. So X is a useful one to know. And that's in command line, X. And I can just keep hitting X. Not the most efficient way, but I can keep doing that. All right, what if I want to delete more? So this leads me to what I call visual mode. It's what Vim calls visual mode. So if I hit the V key, you see this notation down here changes in the lower left-hand corner. It says visual. And I can start moving around and selecting text. And if I hit X now, it gets rid of that whole block. And it's not restricted to lines. I can select a whole bunch of text and then hit X, and then I could go somewhere else and hit P and paste it. So you know how when you do Control X in Windows, what does that do? That's cut. It goes away, but it's not gone, right? Because now it's in the copy buffer, and you can paste it. That's the same thing with X and Vim. X is like a cut. It gets rid of it, but it keeps it so that if you hit P somewhere, it'll paste it. This visual mode is really quite useful, and you can move around in visual mode the same way that you move around in regular mode with the the HJKL keys. And then once you get the piece that you're really interested in, you can X for cut, or you can hit Y, and you see down there in the lower left-hand corner 8 lines yanked. That's copy but not cut. And now I can go down here and hit P and paste. You'll notice when I do these things, I undo them. Does anybody know how to undo? U, yes. So I can undo things in Vim just by, in command mode, hitting the U key. And then if I go back far enough, I'm back to where I can't make any changes. Rachel?
Wait, X is cut and is copy?
Y for yank. Yes?
When you undo, how do you reverse it?
Control R. Yeah, I suppose that's what it is. Redo. I like that. Undo and redo. And the reason that we don't use R is because R is used for something else. R is used for replace. So let's say that I want to get rid of the E and start typing there at the same time. I can hit S for substitute. Let's say I want to, well, let's leave it at that for now. I don't want to overload you guys. So the big things today are the fact that if you're in escape mode and you hit V, you can start highlighting things and doing stuff to the highlighted regions. Like I can hit Y to copy that, and then I can go somewhere else and paste it with the P command. So Y and P are copy and paste. Or I can hit X, and then I can go somewhere else and hit P. Just like I and A, I inserts before the cursor and A inserts after the cursor, P pastes after the cursor, and capital P pastes before the cursor. So if I, for example, grab this line and yank it, if I want it to appear before this line, I hit capital P. If I want it to appear after this line, I hit, well, it won't work. It'll be after the cursor. So it's effectively the same thing. But anyway, capital P, lowercase p, not a good example, but I can't think of one off the top of my head. And let's see, search. One last thing. So you've got a really large file. You're in escape mode, you hit slash. And then you type some letters. And you hit enter. It'll jump you down there. So slash in escape mode. And if you want to find the next occurrence of that, in fact, let's search instead for the word enter, like that. I hit enter and I end up there. If I want to find the next occurrence, I just hit N for next. And if I want to find the next one, I hit N for next. And the next one, N. This is a case-sensitive search. So you have to be careful about that. So if I, for example, search for capital even, I'll end up right here. But if I hit next, I won't end up here. And that tells me search, hit bottom, continuing at top, wraps it around. Go ahead, Jason.
You do that for line numbers too?
Okay, if you want to go to a particular line number, for example, let's say that I left out a semicolon there, and I try to compile it. It says somewhere line 14 there's a problem. I can do colon 14, and it'll put me on the 14th line. And again, the error isn't usually right on that line, but it's usually in the ballpark. That's all I'm going to do for now. I'm going to try to do this at least once or twice a week, just a few Vim tips to get you at least motivated. I don't expect you to walk out of this room and remember all of this stuff, but now you know it's there. And now you can go look at the Vim cheat sheet or the Vim tutorial and try to remind yourself how it worked, or you can come and look at the video. So that's the first 10 minutes of today. Let's break here and let Aiden do his thing. Getting pretty nimble.
Oh, yeah, I'm gonna be a pro pretty soon.
Go ahead and see your...
Sounds good. Actually, can I have the projector?
Can you have it?
Can I use it?
Oh, absolutely.
Oh, is it still working? I don't know if it's still working.
I just muted it so,
okay.
so that you could pull up your email and any sensitive things that are in your inbox will not be displayed for the entire world. Not that I expect there to be anything in there, but it's just common courtesy.
That's fair. Fair enough.
Yeah. So. Hey, you never know what's going to pop up on somebody's computer. Believe me, yeah. Like, a kid asked me for help, and I sat down and he pulled up the program, and the name of the program is "I hate this fucking program." That's CPP.
All right, so we're gonna start off with just an overview of. My question was, who is Bjarne Stroustrup? Stroustrup. It's Danish. He was born in 1950. Currently teaches at Texas A&M, and he is largely charged with inventing C++, the program we use here in class. He started developing it in 1978, and he pretty much did everything from the ground up. He personally made all the definitions, all the implementation designs, and pretty much had the original vision for the programming language. His qualifications: he first did his undergrad at Aarhus University in Denmark, and then later got his PhD in computer science from Cambridge before he came to the US and started teaching at A&M. He is the recipient of numerous awards. The most recent was the Proctor Prize in 2005 for the latest version of C++ that was released then. And now he's basically the father of one of the largest programming languages in the world. It should be noted that in '85 was when he released the first official C++ implementation, when he gave his first demo. And one of the main things that is actually a YouTube video I'm going to play, about 3 minutes, where he answers two really sweet questions. He comes up with this notion of classes, and he goes into that a lot more in the video, but I'll play that for you now. Oh, was that audio? Oh, that would be awesome.
You can just start it.
All right.
Get it squared away.
Here we go. Enjoy.
In the really old days, people had to write their code directly to work on the hardware. They wrote load and store instructions to get stuff in and out of memory, and they played about with bits and bytes and stuff. You could do pretty good work with that, but it was very specialized. Then they figured out that you could build languages fit for humans for specific areas. Like they built Fortran for engineers and scientists, and they built COBOL for businessmen. And then in the mid-60s, a bunch of Norwegians, mostly Ole Johan Dahl and Christian Nygaard, thought, why can't we get a language that sort of is fit for humans for all domains, not just linear algebra and business? And they built something called Simula. And that's where they introduced the class as the thing you have in the program to represent a concept in your application world. So if you're a mathematician, a matrix will become a class. If you're a businessman, a personnel record might become a class. In telecommunications, a dial buffer might become a class. You can represent just about anything as a class. And they went a little bit further and represented relationships between classes. Any hierarchical relationship could be done as a bunch of classes. So you could say that a fire engine is a kind of a truck, which is a kind of a car, which is a kind of a vehicle, and organize things like that. This became known as object-oriented programming, or also in some variants of it as data abstraction. And my idea was very simple, to take the ideas from Simula for general abstraction, for the benefit of sort of humans, representing things so that humans could get it, with low-level stuff, which at that time was the best language for that was C, which was done at Bell Labs by Dennis Ritchie, and take those two ideas and bring them together so that you could do high-level abstraction, but efficiently enough and close enough to the hardware for really demanding computing tasks. And that was where I came in. And so C++ has classes like Simula, but they run as fast as C code. So the combination becomes very useful. Yeah, I say if I have to characterize C++'s strength, it comes from the ability to have abstractions and have them so efficient that you can afford it in infrastructure, and you can access hardware directly, as you often have to do with operating systems, with real-time control, with things like cell phones. And so the combination gives something that is good for infrastructure in general. Another aspect that's necessary for infrastructure is stability. When you build an infrastructure, it could be sort of the lowest level of IBM mainframes, talking to the hardware for the higher level of software, which is a place they use C++, or a fuel injector for a large marine diesel engine, or a browser. It has to be stable for a decade or so, because you can't afford to fiddle with the stuff all the time. You can't afford to rewrite it. I mean, taking one of those ships into harbor costs a lot of money. And so you need a language that's not just good at what it's doing. You have to be able to rely on it being available for decades on a variety of different hardwares, and to be used by programmers over a decade or two at least. C++ is now about 3 decades old. And if that's not the case, you have to rewrite your code all the time. And that happens primarily with experimental languages and with proprietary commercial languages that change to finish fads, to meet fads. C++'s problem is the complexity, partly because we haven't been able to clean it up. There's still code written in the 80s that are running, and people don't like their running codes to break. It could cost them millions or more.
All right. So he kind of generally explains how C++ is a combination between this program Simula and the original C program, where he pretty much takes this organizational categorization and implements it with the C to create C++. And that's pretty much it. Any questions? Sweet. Oh, yeah. Sorry.
I don't know if you know the answer to this, but if musicians get royalties for their music, how does a creator for a program like himself maybe make money in the long run?
Well, I certainly don't know, but I can speculate that maybe he sold the programming for like things like Terminal or Putty or sold some of those rights out. I'm not sure. Maybe Albert knows. Probably made none.
The money that he makes from it is from Texas A&M
Yeah.
being really happy that he's famous.
And his textbooks.
They give him extra money and raises because he's such a great professor. That's it.
Yeah, he comes out with a new edition of his
It's
C++
also
textbook.
the reason that C++ is so widely used.
Yeah.
Right? Because it's an excellent language and it's free. Okay, thanks, Dave.
Alrighty. So let's talk briefly about homework 3. My hope is certainly by the end of Wednesday you'll have the tools necessary to do homework 3. Homework 3 comes with a rather lengthy preamble that describes this particular sequence called the hailstone sequence. And it looks like scary math, but it's not too bad. What you do is you start off with some initial positive integer, and you just go through a loop like a computer. You start with n0 and you ask yourself, is n0 even? If it's even, then to get the next number in the sequence, just divide it by 2. That makes sense. And if it's odd, well, you can't divide it by 2, right? It's not going to divide evenly anyway, so you have to do something else. So in this case, what we do is we multiply it by 3 and we add 1. Okay, why? Well, there's nothing particularly interesting about this sequence other than the fact that it's the object of a famous conjecture due to Collatz. The Collatz conjecture is that the hailstone sequence terminates for every positive integer. It's a conjecture because it's an open question, sort of like Fermat's last theorem was for the last 300 years until Andrew Wiles came along and proved it in 96, 97. This is an open question in mathematics. It's been tested to very, very high numbers and has not been shown to be false. In fact, experimental evidence shows it's true for up to, 5 times 10 to the 18th. And it's probably even further than that now because who knows how up-to-date Wikipedia is. But you get the idea. This has been tested, but it hasn't been proven. Maybe there's some number out there for which this sequence does not terminate. Why is it even interesting that this does terminate? Well, if you look at this thing, you have two possibilities. In one case, the number gets smaller, right? How is this thing going to terminate? It's going to terminate if it ever equals 1. So you start out with a 10, say. Is 10 even? Yes. Then divide it by 2. Now you're looking at 5. Is 5 even? No. Then multiply it by 3 and add 1. Is 16 even? Yes. Divide it by 2. Even? Yes. Even? Yes. Even? Yes. Terminates. Once it gets to 1, it stays at 1. That's what this extra condition up here is. Collatz conjecture is that any positive number you choose will end at 1. The reason it's interesting is because there are opposing forces in this formula. In one instance, the thing wants to get smaller, divide by 2. And in the other instance, the thing wants to get bigger, multiply 3 and add 1. So sometimes the sequence is going down, other times the sequence is going up. So you can just stare at this and think, I don't know what's going to happen. Maybe it just goes up forever. But it doesn't. It always goes down eventually to 1. Okay, so we'll leave the conjecture to Collatz. All I care about for this assignment is you to write a loop that generates the sequence and tells me how long it is for a particular initial point. So for example, this sequence starting with 10 is 1, 2, 3, 4, 5, 6 steps long. So the length of the hailstone sequence for 10 is 6. Let me show you my program. Let's go here. Didn't realize I'd logged out. So here's what your program will do. This program will compute the length, yada, yada, yada. Enter N0. I'll plug in 10. Would I like to see the terms of the sequence? Sure. The hailstone sequence is this, and it has length 6. And that's consistent with what I've written here, 10, 5, 16, 8, 4, 2, 1. 10, 5, 16, 8, 4, 2, 1. Many of you can probably already imagine the internal workings of this program. There's a loop. You're asking for the number, then you drop into a loop, which actually applies the rules successively, and then when it gets to 1, it stops. And we'll talk more about that, but I think a lot of you have an intuitive idea of how this thing works. It's kind of fun to play with. Let's look at 11. So there's 11. Let's look at 12. So 12's sequence is actually shorter than 11's sequence. What do you notice about this sequence as I go through this?
8, 4, 2, 1.
It does seem to always want to end in 8, 4, 2, 1.
8, 4, 2, 1. 5, 16. Oh my gosh, yeah. 10, 5, 16, 8, 4, 2, 1.
So it raises an interesting question. What if I try, for example, 3?
Well, it's going to go to 4, 2, 1, right?
I don't know. Oops, 3.
Whoa.
So yeah, 3, 10, 5, 4, 2, 1. What else is missing from those low ones? 7 is not there, right? Oops. So 7 is really painful for this sequence for some reason. It has to work really hard to get back down to, and notice the 10's not in there, right? It's just 8, 4, 2, 1.
It's 10, 5.
Oh, sorry, 10, 5, yes, okay, it is in there. I take it back. Well, and that's an interesting question. Does it always end in these, in the 10, 5, 16, 8, 4, 2, 1, or can you find a different ending?
What do you use here to just take the length?
We'll talk about that as I go on. I just have a little counter variable that counts how many times it goes.
It wouldn't do that for 2, right? So it should be 2.
Yeah, 2 will be boring. Well, I don't know. I guess it depends on how exciting your life is. Okay, so it's an interesting sequence. Your above and beyond can be pretty wide open here. I just want you to play around with it. Think about it. You could even tweak the formula a little bit. See if you can get some other kind of interesting formula or observation. You could maybe try to find the longest hailstone sequence for numbers up to 100, starting numbers up to 100. And there's lots and lots and lots of above and beyond here. And I look forward to seeing what you might come up with. That said, I leave you with the last sentence here. And it looks like, based on the picture here, that you're always going to end up 168421. And there's different ways to get to 16. So the 10 and the 5 are not always there. But it looks like 168421. Powers of 2, yeah. Powers of 2. And the strong Collat's conjecture I like too. States that this holds for any set of obsessively hand-applied rules. I'll let you think about that for a while. All right, so that's where we're headed. Let's go on and continue to talk about Boolean expressions. So a really important part of any computer program is the ability to branch and deal with contingencies. We've seen a little bit of that already. Have we? Yeah, we have. The quadratic equation solver. What are some contingencies that thing has to deal with? Go ahead, say. So the discriminant, right? So it really had 3 major contingencies. D positive, D0, D less than 0. And it had to behave dramatically differently for each of those different cases. If you didn't have if statements, you'd be kind of in trouble, right? It would not be a very useful language. If statements are, the behavior of if statements depends on what we call Boolean expressions. Okay, Boolean expressions are, for lack of a better term, statements that evaluate to either true or false. The name goes to a mathematician in the mid-19th century, George Boole, who, unbeknownst to him or his contemporaries, decided to really focus on algebras of bits, things that are either 0 or 1. Boole was interested in how this connected to formal logic. Little did he know in the 20th century it would be the foundation of much of computer science. So Boolean expressions, George Boole, statements that evaluate to either true or false. For example, if D is the discriminant from our quadratic equation formula, then this sequence is a Boolean expression. We don't know what D is when we get to this point. It depends on the user input. But we do know that when C++ or when the program gets to this point, that expression will evaluate to either true or false, right? So it's a Boolean expression. So far, let's see, we've used, in fact, so far I think these are the 3 that you've used. Those are the 3 Boolean expressions that you've used. And presumably you could do it for other variables as well, test, that sort of thing. Oh, we've also done this one. And maybe we've done some other ones, right? So these are all Boolean expressions, but they're the simplest kind. They're just one atom, either true or false, right? This whole thing collapses to either true or false. This collapses to true or false. And they're pretty simple. Boolean operators are ways of combining expressions to get new expressions. And there are three big Boolean operations that we'll talk about today: the and, or, and not operators. So and in C++ is represented by two consecutive ampersands, no spaces in between them. Or is represented by two vertical bars, again, no spaces between them. The vertical bar, in case you're wondering, is the symbol above the backslash key on your keyboard. And the not operator is an exclamation point. That's the symbol above the 1. How do these guys work? Well, these two guys are binary operators. And this is unary. So this acts on two things. It acts on two Boolean expressions, and this acts on one. But the question is, how do they act? And they act in very well-defined, clearly defined ways. So the AND operator works like this. I'll use T for true, F for false. There are four possibilities, right? Remember that the binary, that this thing works on two things. So you'll have true or false to the left, true or false to the right. And the way that it works is true and true is going to be true. True and false will be false. False and true will be false. And false and false will be false. So if you take something that's true and you AND it with another thing that's true, you'll get something that's true. If you take something that's true and you AND it with something that's false, you'll get false. And in fact, all other situations give you false. So this one's pretty strict. This one, the OR operator, on the other hand, is fairly generous, fairly liberal. So if you take two things, one is true, and you OR it with another thing that's true, you'll get something that's true. If you OR it with something that's false, it's still true. If you take something that's false and you OR it with something that's true, it's still true. And the only thing that's going to give you trouble, and not really trouble, but if you do false or false, you get false. Go ahead.
So it's not really or, it's and or? It's just seen as or?
Rephrase.
When you're just using the or operator, in the English language, it'd be and or, and slash or, right? Because and still works.
It's an inclusive or. Yeah, he's saying when both are true, it still works.
Right. Yes. Yes.
And the symbol for or, those aren't two slashes.
Those are two vertical bars,
Vertical bar, yeah.
and it's and the symbol is above the backslash key. Okay, and the last one, the unary operator, not, you might guess. Not true is false, and not false is true. All right. Let's talk about a couple of examples here. Let's suppose we want an expression. Let's say we want true if 0 is less than x is less than 1, and false otherwise. So we want something that's true if x is between 0 and 1 strictly, and false otherwise. The C++ expression for this would look like the following: x greater than 0 and x less than 1. And if you want, you can put parentheses around each of these just to remind you that those things are happening first. Now, again, I don't know what value x has when I get to this point in my program. But if x is, say, 5, this will be true, right? And if x is 5, this will be false. What's true and false? True and false is false. So it's a way of, for example, in this case, making sure that x is between 0 and 1. So let me write that example out explicitly here. Let's suppose that x is 5. Then what we have is true and false, which is false. And that's a good thing, right? Because 5 is clearly not inside that range 0 to 1. How about if we do x equals 1? So what's the first Boolean expression? True. And the second? False. So it's still false. How about if we do x equals 1/2? First one, and true. So that's true. Okay. All right, what if we want true if x is less than or equal to 0 or x is greater than or equal to 1? So build it for me. What's the first expression? So we're going to use or here, right? Okay. X less than or equal to 0, and then the two vertical bars, or x greater than or equal to 1. And let's do a few examples here. Let's suppose x is equal to 5. What's the first expression? That's false. Or the second expression? And that means the thing is true. True if x is less than 0 or x is greater than 1. Either one of those conditions is okay. X equals -1, that's true, or false, which is true. How is this example related to this example? Yeah, this is the complement, right? In a sense, the logical complement of the first statement. And in fact, an equivalent way that we could have written this I have no idea if it's E or I. I think it's I. I don't know. So since this is the logical complement of the first example, we could put a big old set of parentheses around the first one. And then we could put an exclamation point in front of it and get the exact same thing. So that C++ expression is exactly equivalent to that one. In fact, this is an example of a famous logical identity. Does anybody know what it is? It's not really important to this class, but I can't let it pass without note. This is de Moivre's identity. Okay. Questions about that? Yeah, Aiden.
Does the exclamation point always go in front of that expression?
It goes in front of whatever logical expression you're trying to invert. Absolutely. So it doesn't go after, it goes in the front. Boy, I can't remember what I was going to say. All right, let's talk a little bit about Boolean variables. So again, I've talked a little bit about this, but it's really up to you guys to read and look at the examples in the book and really understand them. So what we see here is the beginnings of being able to build much more sophisticated decision tools, decision-making processes. Even this one's a pretty simple one. Just note here that you can't do something like 0 less than or equal to x less than or equal to 1 is not valid C++ syntax. C++ will just throw an error, or it might even not throw an error. So you have to be aware of this. That if you want to, say, test whether a variable is between two other values, you actually do have to do it the long way. You have to build greater than or equal to 0 and less than or equal to 1 separately, and then put them together with the AND operator. It doesn't understand this shorthand notation that we all learned in algebra. Okay, with Boolean expressions comes a data type that I haven't had a chance to talk about yet, but there's a Boolean data type. So you can do bool p, and this defines a variable. It defines a variable p of something that is either true or false. You could actually make it have a value, and this is legitimate C++ syntax. So I can write something like p equals false, and that will set that variable to false. And furthermore, down the road, I can do something like if p, then do some stuff. And this will execute if p is true, and skip if p is false. Sometimes it's useful to actually take an expression, for example, some kind of Boolean expression, p equals x greater than or equal to 1, or x less than or equal to 0, and actually store it in a Boolean variable, because maybe you want to use that expression in a few different places and you don't want to have to keep writing the expression over and over again. So you take its value, remember this turns into something that's either true or false. You're going to take that thing and store it in this Boolean variable, and then you can use it in lots of different places. Okay, questions about that?
So it doesn't store the number, it stores true or false?
It stores true or false, and it's something that then can be used in an if statement or a while loop or something like that.
I thought it stores just that formula.
Nope. It stores whatever that formula turns into, true or false. So x has a certain value. Let's say x is 5, right? So you come down here and x is 5. This is true, right?
Oh, so x will already be defined.
Right. Right. So x already has a value due to something that happened above.
So x is stored as 5.
Yeah, let's say it's 5. It comes down here. This is true. This is false. True or false is true, and a true ends up in p. And then, yeah, maybe I would have an if statement later on that will run if P is true and won't run if it's false. In fact, I can show you an example. Yeah, really quickly. A really common thing to do would be, say, let's have a bool run equals true. And then you could do, down here, you would do something like while run. And then maybe we'll do cout enter an even number. And then cn n. And then maybe we'll do if n% 2 equals 0, then we'll just set run equal to false. Else okay, what's going to happen here? So I set run equal to true, way up at the top, and then somewhere in the middle I need to get my hands on an even number from the user. When it gets here the first time, what's run? True. So the while loop will run. It'll go. It'll run. So then this prints out, and then the user presumably types in a number, and then we read it, and then we test it. And if it's even, run equals false. Now it skips this, right? Because that's the else part of this if statement. It skips this. It goes back up here. What's run? Now it's false, and I move on. I stop the loop. On the other hand, let's say I enter 5. This is false here. So this line happens. It puts out a friendly prompt, and then run is still true, right? And I go back up here and I run it again. And there's an example of using a Boolean variable to control a while loop. We'll talk more about these loops on Wednesday. See you then.